Let's talk about logistic regression. It's one of those true workhorses in machine learning. It's kind of quietly running in the background of everything from your bank's fraud detection to cutting-edge medical diagnosis. Today, we're going to pull back the curtain and see exactly how it takes a huge pile of data and turns it into a real, actionable decision.
Think about it for a second. Is a customer actually going to cancel their subscription? Will a patient respond to this new treatment? Is that credit card swipe legit? Now, a simple yes or no is fine, but what if you could know the chance of it happening? That's the real power, right? We don't just want a binary answer, we want to know the odds.
And that is exactly where logistic regression shines. Instead of just drawing some hard line in the sand between yes and no, it gives us the probability of an outcome. And the secret weapon it uses to do this? It's a surprisingly elegant S-shaped curve.
So, how on earth do you take any number, any number, positive, negative, huge, tiny, and just swoosh into a neat probability between 0 and 1? Well, you use this thing, the logistic function. You'll also hear it called the sigmoid function. It is the mathematical engine that drives this whole process.
And check this out. This is that magic in action. See how on the left, as the numbers get really negative, the curve just flattens out, getting super close to 0. And on the right, as they get really positive, it gets closer and closer to 1, but it never quite touches either. Everything in between? Well, that's the interesting part. That's the maybe zone.
Okay, so we've got the right tool, this S-curve. But a generic curve isn't going to cut it. We need to mold it to get it to fit our specific data perfectly. We have to find the absolute best version of this curve for the problem we're trying to solve. This brings us to a really core concept called maximum likelihood estimation, or MLE for short. Now, it sounds complicated, but the idea is actually super intuitive. It's just the process of finding the right numbers, those parameters on the slide, that basically tune our S-curve to be the best possible fit.
So MLE kind of works backward. It looks at all the data you already have, all the yeses and nos from your training set, and it asks this simple question. What shape of S-curve would have made the data I'm looking at right now the most predictable, the most likely thing to have happened? And then it finds the exact settings for that curve. Now here's the catch. Trying to maximize that likelihood function directly means you have to multiply thousands, maybe millions, of tiny little probabilities together. And that creates a huge headache for computers. But luckily for us, there's a really, really clever workaround. Just picture it. You've got thousands of data points, and the probability for each one is some number between 0 and 1, right? When you multiply all of those together, the final number gets unbelievably small. So small that computers can literally run out of decimal places to keep track of it. It's a problem called floating point underflow, and your result basically gets rounded to 0, making the whole calculation useless.
The solution, as you can see here, is to switch from likelihood to something called log likelihood. By taking the logarithm, we completely change the game. Thanks to a neat little math rule, what was a gigantic, messy multiplication problem, well, it turns into a simple addition problem. And that is something computers can handle beautifully. And here is why this trick works so well. The logarithm function is monotonic, which is just a fancy way of saying it always goes up. Because of that, the highest point of the original function happens at the exact same spot as the highest point of the log of that function. So we get to solve a much easier problem and still get the exact same answer. Pretty clever, right?
So our task is clear. Find the peak of this log likelihood function. But here's the problem. There's no simple formula that just tells us where the top is. We can't just teleport to the summit. We have to climb it, step by step. And this is where we enter the amazing world of numerical optimization. We're talking about algorithms that are built for exactly this kind of thing. They start somewhere on the function's surface, take a step uphill, look around, take another step uphill, and just keep doing that until there's nowhere left to go up. They're basically our digital mountaineers. But just like climbing a real mountain, your strategy matters a lot. A lot. Do you just take tiny, careful steps based on the slope right under your feet? Or can you somehow sense the overall curvature of the mountain to take a smarter, more direct path to the top? This exact question is what led researcher Thomas Minka to compare a bunch of different algorithms to see which climbing style was actually the best. So, here are the main contenders lining up at the starting gate. You've got some classic, famous methods like Newton's method, and then some more specialized ones like iterative scaling. They all promise to get to the top of the mountain, but the big question is, who's going to get there fastest?
So Minka set up this computational horse race. He pitted these algorithms against each other on some big data sets to see how they really performed in the wild, measuring not just if they got the right answer, but how much work it took to get there.
In the very first test on a pretty standard, well-behaved data set, the differences were, well, they were staggering. The performance gap between the fastest and the slowest wasn't just, a few percentage points. It was more than 2 orders of magnitude. The winners, conjugate gradient and BFGS, were over 100 times more efficient than the slowest methods. Let that sink in for a second. 100 times faster.
Okay, so for the next race, Minka made the mountain way harder to climb. He used what's called highly correlated data. That just means you have features that tend to move together, kind of like a person's height and their weight. This creates a much more complex, warped surface to climb, and it's where the really good algorithms showed what they're made of. And on this tricky terrain, a clear pattern emerged. The best climbers were the ones that could sense the mountain's overall shape. They use something called the Hessian, which is basically a map of the curvature. This allows methods like BFGS to take these big, intelligent leaps towards the summit, while the other algorithms that can only see the slope right in front of them get totally lost. So the bottom line is this. Minka's research gives us a crystal clear verdict. For just general purpose, fast optimization, conjugate gradient is an awesome choice. But if you think your data might have those complex relationships, a Hessian-based method like BFGS is the undisputed king of the mountain. And those older methods, they're just completely left in the dust. And this isn't just some academic race to save a few seconds of computer time. A 100x speedup is the kind of leap that makes training models on billions of data points actually possible. It's what lets us tackle problems that just a few years ago would have been computationally unthinkable, which really makes you wonder, what's the next impossible mountain we're now ready to climb?